This video is the first where we're beginning to look at the first theory of bonding that we're going to cover in this class, and that has to do with Lewis structures and molecular shape. So in order to understand molecular shape, which is the ultimate goal of this whole thing, because if we can know the shape of molecules and whether they have polarity or not, for example, this can help us understand the physical properties and the chemical properties of molecules. But we have to build up to this slowly. And this begins with understanding two concepts. One concept is electronegativity, and that leads to this other idea of bond polarity. So in this video, we're going to be focused on covalent bonds. We're going to look at nonpolar and polar, but we're also going to bring ionic bonds back into the picture as well. So first, an overview of the three bonding theories we're going to cover in this course. These bonding theories are each in their own way help us predict the circumstances under which bonds form and the properties of molecules that result from that bonding. So chapters 4 and 5 are focused on Lewis theory and VSEPR. These theories can help us predict molecular shape, polarity, other physical and chemical properties, reactivity. And Lewis theory and VSEPR stands for valence shell electron pair repulsion theory, and we'll get to that in a later pre-class question set. But what these do is they really help us visualize what's happening with molecules. These other two theories, valence bond theory and molecular orbital theory, they're more accurate theories in the sense that they can explain more of what is going on with molecules. Whereas Lewis theory and VSEPR, they're more limited. There's a lot that they can't explain. But the trade-off is that it's easier to visualize molecules when you're dealing with Lewis theory and VSEPR, and it gets increasingly more difficult to visualize molecules in a way that's tangible to us as humans, and we can't see these molecules. When we look in the air, we don't see anything, right? So molecular orbital theory is by far the most accurate, but it's also the hardest to visualize. And as we move from Lewis theory to molecular orbital theory, we also move from the idea of matter as a particle, which is really what we're focusing on for Lewis theory, to matter as a wave, which is the focus of molecular orbital theory. And valence bond theory falls somewhere in between. It has elements of Lewis theory, and the visualization is more difficult but isn't horrible. But then it also has elements of quantum mechanical theory, which is kind of what it shares in common with molecular orbital theory. So, focusing on the Lewis and VSEPR theory first. Electronegativity is a very important concept that helps us understand the types of bonds that exist. Are they polar covalent? Are they nonpolar covalent? Or are they ionic? So electronegativity is the ability of an atom to attract electrons to itself in a chemical bond. And the different electronegativities of the different atoms involved in a given bond results in different degrees of electron sharing, or if we're dealing with ionic compounds, transfer. This concept was initially suggested by a chemist, Linus Pauling. So there's a picture of him. And this is based, the concept of electronegativity is based on observations he made about bond energy. So bond energy is the energy required to break a chemical bond. And the questions he started to ask when he looked at the bond energy of different bond types are, why are ionic compound bonds harder to break than molecular compounds? And this led him to the idea and the concept of electronegativity, because it helps us understand the answers to that question. So the way things are set up, and I'll show you a periodic table on the next slide, is that fluorine is the most electronegative atom. That's an observation that was made. And it was arbitrarily assigned an electronegativity value of 4. So it's not completely arbitrary. The reason it was given a value of 4 is because some of the least electronegative atoms on the periodic table end up with electronegativity values that are greater than 0. So if fluorine was assigned a value of 2, for example, the least electronegative atom on the periodic table, which is francium, Fr, it's in the lower left-hand corner of the periodic table, it would actually have a negative electronegativity value. So the goal was that the electronegativity value, the En value, assigned to all the different elements in the periodic table should all be a positive value. So fluorine, it's the highest, so it was given the highest value, but this number of 4 is somewhat arbitrary. It's not based on a measurement. That 4 does not come from a measurement. It's just a way to compare different elements to each other in the periodic table. So here are periodic trends in electronegativity. What you can notice is it increases across a row. So as you go from left to right in the periodic table, you see that the electronegativity increases. And then as you go down a column from top to bottom, you observe a decrease. So you can think about atomic radius, which is something that we already studied. And the atomic radius trends are the opposite. So when you go from left to right in the periodic table, remember that the atomic radius decreases, and that when you go down a column in the periodic table, the atomic radius increases. And these two things are inversely or indirectly related to each other, but there's a reason for that. And it all has to do with electron shielding and the charge in the nucleus, the effective nuclear charge. So let me explain that a little bit more. Let's look at fluorine, and we'll contrast fluorine, which is the most electronegative element, to francium, which is one of the least electronegative elements. So with fluorine, you have something that looks like this. It's in row 2. So you've got the nucleus, and you've got an n equal 1 and an n equal 2 orbital. So n equal 2 is the outermost orbital. Here, fluorine has, let me get my other periodic table, it's got 9 protons in its nucleus. And it's the smallest. Remember, as you go across a row, if you go back to oxygen, oxygen only has 8 protons in its nucleus. So oxygen has the less ability to pull the electrons in that n equal 2 level towards it. So this is, fluorine has got the smallest atomic radius because it's got a high charge and an n equal 2 energy level. But that means it has the highest electronegativity. So if electronegativity is the ability to pull electrons toward it from other elements that it's bonding with, the reason fluorine has the highest is because it's got the least amount of electron shielding, because it's only got n equal 2 as its energy level. When we look at francium, we'll see that it's got way more energy levels. And it's also got the highest effective nuclear charge, one of the highest for its for the electrons in that outer orbital. So because it's got these two things going on, for any other atom that approaches fluorine and tries to bond with it, fluorine is going to pull the electrons from the other atom toward it the most strongly, because it's got this really high effective nuclear charge due to the combination of having this charge of plus 9 plus in the nucleus plus a very low amount of shielding. So let's contrast that with francium, which has a very low electronegativity. So again, electronegativity is the ability of an atom to pull electrons toward it from a different atom that it's bonding with. So francium, you've got your nucleus, and for francium, you're in row 1, 2, 3, 4, 5, 6, 7. So you've got 7 levels. So 2, 3, 4, 5, 6, and I'm just going to rewrite francium here. You get the idea. So what's happening here is, even though francium has 87 protons, it's a high number. I mean, it's way bigger than 9, right? Which is what fluorine has. It's got n equals 7 energy levels. And you know that by the time you get down to francium, you have d orbitals involved, you have f orbitals involved. D orbitals hold 10 electrons, f orbitals hold 14 electrons. And then this is also including all the s and all the p orbitals. So there are a lot of electrons between any atom that approaches francium, the electrons of that atom. So I'll just put electrons of other atom. There are a lot of electrons in here, in between this electron and that positive charge in the nucleus. So the reason bonding is happening is you've got this attractive force between the electrons of another atom and the nucleus of the one it's trying to bond with. So there's a ton of shielding going on here. So that means francium has the lowest ability to pull electrons toward it, which is why it has the lowest electronegativity value of all the elements in the periodic table, in addition to cesium. Cesium is also 0.7. And then the atomic radius relationship is opposite again, because look how big the radius of francium is because of all those energy levels. It's a big radius for that element. So that's why you see the trends that you do in the periodic table. So now that we know something about electronegativity, we can start to look at the polarity of a bond between two different atoms. So we're going to use electronegativity difference, or delta N, to determine what type of bonds we have. So notice that if the electronegativity difference between two atoms is between 2 and 3.3, one of the two atoms has enough of a pull on those electrons to create an ionic bond. It's enough of a pull that the electrons are essentially transferred. They're not shared. So remember, in ionic bonds, electrons are transferred. If the electronegativity difference between two atoms in a bond is less, you get covalent bonds. So there are two different types of covalent bonds. Remember, in covalent bonds, electrons are shared. So what that means is neither of the elements or the atoms of the elements involved in the bond has the ability to pull the electrons toward it so strongly that there's actually going to be an electron transfer. It's shared in both cases. When you have a polar covalent bond, you've got unequal sharing, meaning that one of the elements involved, the atom of one of the elements involved, pulls the electrons toward it more strongly in that sharing. So when it's pulled towards it more strongly, it gains this partial negative charge, which is this delta minus symbol. So whatever this element is, the electrons in that bond, and they're shared between the two elements, they spend more time near it, or get pulled closer to it slightly than this other element. And because the electrons are pulled slightly away from this other element, whatever this blue one is, it's experiencing a slight positive charge. So you don't get the full negative and the full positive charge like you do with ionic bonds, but you get a partial negative and a partial positive. And what this is showing, these partial charges with these delta symbols, is again that electrons are shared. They're not fully transferred like they are in ionic bonds. And then if you have this same element, you've got equal sharing because they've got the same electronegativity value or something very similar. So anything between 0 and 0.4 is going to be what's called a non-polar covalent bond. When there's no or very little pull on electrons by one of the two atoms involved in the bond. So these are the three types. I've got three examples down here. So what types of bonds? First, we'll do the OH in water. So if we draw the water molecule, it looks like this, and you're going to learn over the next week or so how to actually figure out this structure. So it's got an oxygen and two hydrogens, and it's got this bent shape, and you're going to understand that over the next week or so, why that is. But for now, we just want to look at bond polarity. So there are two bonds in this water molecule. Both of them are OH bonds. So that's the bond we're interested in. They both have their own polarity. In this case, if we go back to that table of electronegativity values on the previous slide, we can see that oxygen has an electronegativity value of 3.5 and hydrogen is 2.1. So 3.5 and 2.1. So we can look at the electronegativity difference. So we're just going to do 3.5 minus 2.1, and that means the electronegativity difference for an OH bond in a water molecule is 1.4. So this value falls in here. It's between 0.4 and 2. So that means the water molecule is classified as polar covalent. That OH bond in the water molecule is classified as polar covalent. So let's look at another example, methane. So methane looks like this. You've got the carbon in the middle, and you've got 4 hydrogens around it. So there are 4 bonds here, and we want to look at CH bond specifically, and that's the bond type in every case. So each of those bonds has a polarity. So again, what we want to do is look at the electronegativity difference between the two types of atoms involved in that bond, the carbon and the hydrogen. So again, if we go back, carbon has an electronegativity of 2.5 and hydrogen is 2.1. So what we can do here is 2.5 minus 2.1 is going to give you 0.4. So this is the electronegativity difference between the carbon and the hydrogen in that CH bond. So notice it falls right on the line here. So what I generally tell students as a guideline here is nonpolar covalent, categorize that as electronegativity difference between 0 and 0.4. And then for this group, we can say 0.5 to 2, just 1/10 of a unit above that 0.4. So these are somewhat arbitrary cutoffs, and I want to call your attention to this word continuum. So it's really a continuum. You've got ionic bonds, up here in this region. But you've got, within this region, you could say something that has an electronegativity that falls somewhere here versus another compound that's got an electronegativity that falls there. This bond is more ionic than this bond, right? And it's a continuum. You can say the same kind of thing. So we've got the most purely equal electron sharing on the left-hand end of the spectrum, where we have a delta En of 0, to the most complete electron transfer you can have of 3.3, and the most ionic a bond can be. So it's a continuum. So these breaking points are somewhat arbitrary. So we can classify methane, the bonds in methane, the CH bonds in methane, based on that criteria as nonpolar covalent. And then we can look at this last case, lithium oxide. That is an ionic compound, so it's not in a molecule form like the water is and like the methane is. It's in a lattice. And I'm not going to draw the lattice, but what I'm going to do is just look up the values here and show you how it's ionic. So lithium is 1, oxygen is 3.5. So that means the electronegativity difference is 2.5. And when you have a difference of 2.5, it falls between this range of 2 and 3.3. So that means lithium oxide is ionic. So determining bond polarity is going to help us later to determine molecular polarity. They're two different things. So representing bond polarity. There are two possible notations. So here's the Lewis dot structure for hydrogen fluoride. We're just looking at, here's the chemical formula would be HF. So Lewis dot structure, we're going to learn how to draw these in a little bit. To denote polarity, you can do an arrow with a plus sign on the tail. So here's the plus sign. So the way to think about this is fluorine has a higher electronegativity than hydrogen, so the electrons are being pulled toward it. And then this is, you're left with a partial positive charge on hydrogen because the electrons are being pulled away from it. So that's one way to think about it. And then here, you've got the partial positive and the partial negative charge written with the delta symbol. So you can represent bond polarity either way. For these examples that we did, if we look at the electronegativity values, oxygen has a higher electronegativity value than hydrogen. So for both of the OH bonds in water, it's gonna look like this. So that means in this water molecule as a whole, the electrons are generally being pulled more toward oxygen from both of those hydrogens. And the hydrogens are going to end up with the partial positive charge. And on this end of the molecule, you're going to have a partial negative charge. Methane, same kind of thing. Each of these bonds has a polarity. Carbon has a slightly higher electronegativity than hydrogen. So the electrons are going to be pulled toward it. Even though the molecule as a whole ends up being nonpolar, and we'll get to that in the next pre-class question set, understanding molecular polarity. Remember, bond polarity and molecular polarity are different. There's still polarity in each bond. A molecule as a whole can be nonpolar, but the bonds still have polarity. So I'm going to write that down because it's important enough to note. So molecules, I'm going to write nonpolar molecules. Can have, and often do in a lot of cases, can have bond polarity. We're getting ahead of ourselves with the concept of molecular polarity, but I want you to remember this. Nonpolar molecules can have bond polarity, unless it's the same element, like a nitrogen molecule. There's no bond polarity here because you're dealing with the same element. But anytime you have different elements, you can have some kind of bond polarity. Okay. Okay, you win. I'm moving on to the next slide. Oh, one more thing. Lithium oxide. This concept of representing bond polarity is not relevant. You don't write lithium oxide like this because it's an ionic compound and you have a transfer of electrons. So the way to represent these would be lithium with the full positive charge and oxygen with the full negative charge. And I just realized this compound is incorrect on these slides because oxygen has a charge of 2-. Okay, so some terminology that's going to be used here when we start talking about molecular polarity. So heteronuclear diatomic molecule, that's a mouthful. All it means is, so hetero is atoms from different elements, and diatomic just means two atoms. So we've got two atoms from different elements in a heteronuclear diatomic molecule. So an example is nitrogen monoxide. You've got two different elements, nitrogen and oxygen, but you've only got two atoms. Another type is homonuclear diatomic molecule. So homo means same, so atoms of the same element, and still diatomic means two. So two atoms of the same element. So you've got two atoms of nitrogen, same element. This becomes important because when you have heteronuclear or homonuclear diatomic molecules, you do not have a molecular shape. So I'm just going to write no molecular shape. When we get to the VSEPR theory, helps us figure out what the shape of a molecule is once we know the bond polarity and can draw the Lewis dot structure. But when you have these types of molecules, you don't have a molecular shape. You have a bond polarity in some cases is present, but you just don't have a molecular shape. So the place that bond polarity is present would be when you have two different elements involved. There wouldn't be any bond polarity here because it's the same element and it has this same electronegativity. Both of those atoms have the same electronegativity. So dipole moments, these are two different ways to talk about bond polarity. Dipole moment and percent ionic character. You do not have to know how to do the calculations for dipole moment. It's a concept that's good to be aware of, but don't worry about doing the calculation. It's quantified, it's measured in a laboratory, like in an instrument like this. This is a giant instrument that's used to measure the dipole moment of different bonds. And just all you need to realize is that the greater the electronegativity difference, the larger the dipole moment. So looking at this, you have large dipole moments here and small dipole moments here. Your book goes into a lot more detail about calculating it and a few other things. All you need to know is the correlation here. The greater the electronegativity difference, the larger the dipole moment. Dipole moment is about charge separation. So the greater the electronegativity difference, the larger the charge separation, because you have one element involved in the bond that's pulling the electrons closer to it, so the charges are separated a little bit more. So going back to what we've already determined, we've determined that the OH in the water molecule is a polar covalent bond. We've determined that the CH in the methane molecule is non-polar covalent. And we've determined with lithium oxide that you have an ionic bond. So lithium oxide has the greatest charge separation. So it's going to have the greatest dipole moment. Non-polar covalent bonds like methane have the smallest dipole moment, and then water falls somewhere in the middle. Another way that electronegativity difference is talked about is as percent ionic character. So this is the second way to talk about bond polarity. So percent ionic character is technically defined as the ratio of a bond's actual dipole moment to the dipole moment it would have if electrons completely transferred. So you can see how that can lead to percent ionic character. The higher the percentage, the more ionic the bond. You do not need to know how to calculate this. You just need to know how it's correlated with electronegativity difference. So look here, the higher as electronegativity difference goes up, the percent ionic character also goes up. And what you can notice here is these are all ionic bonds. Notice that no bond is 100% ionic. If a bond was 100% ionic, electrons would be completely transferred to one of the elements, and that can't happen because if an electron completely leaves an element for another one, that element has no reason to stay. For example, electrons in potassium, there's a transfer, looking at this compound here. Potassium has a +1 charge, fluorine's -1, so there's one electron donated to fluorine when that potassium fluoride compound forms. If that one electron completely left potassium and was no longer attracted to the potassium nucleus, then potassium would have no reason to stick around. It would just leave. So that's why you never have a 100% ionic bond. And notice also, these are all covalently bonded compounds. None of them has a perfect non-ionic character. Hydrogen chloride, HCl, has a higher percent ionic character than IBR. So you can talk about the ionic character of a covalently bonded molecule. And that's it.